Yo, what's up, everybody? All right, this is what we're going to do. We're going to take a brief look at the synapse. We're going to talk about what a synapse happens to be, the parts of a synapse, and all that weird terminology that people use to describe what's going on at a synapse. Now, once again, I'm going to warn you that I'm going to talk about things in this video as if you are currently either studying this stuff, reviewing this stuff, or if you just walk out of class and you're scratching your head and you're looking like one of those minions off of Despicable Me talking about something, say what? You know, like that. So if that's you, then you'll benefit a lot from this video because that's what we're going to do. And I'm going to only stick to about 3 slides. That's it. I'm going to just talk from about 3 slides and really narrow the focus and bring things home as to what we should be understanding about a synapse. So let me get the screen share up and we'll hop right to it. And what I really want to start off with is just one particular slide that I've got here that I think will be very beneficial. And this slide says this is the activity at the synaptic knob. And I want to start off by saying that there's a lot of different names for the structure. Some people call it a synaptic knob. Some people call it a synaptic bulb. Some people call it a terminal bulb. Some people call it a terminal end. I've heard a lot of different names for this thing. For the sake of argument, okay, so please, for the sake of argument, I know that depending on the textbook and the instructor and who taught you and what state, university, nation you took your class in, that's going to determine the name of that structure. But for the sake of argument, we're going to just use one name right now, and that is synaptic knob. And when it says activity at the synaptic knob, it says here that there's calcium concentration gradient established by the pump because there's more calcium outside of the synaptic knob than inside the synaptic knob, and that there are voltage-gated calcium channels that are triggered by a propagated action potential that causes movement of calcium ions into the synaptic knob. So right here at this moment, something you need to understand. The action potential has not reached the synaptic knob yet. And before the action potential reaches the synaptic knob, there are more calcium ions outside of the cell, outside of the synaptic knob, than there are calcium ions inside of the cell, inside of the synaptic knob. Therefore, because there are more calcium ions outside than there are inside, we can assume that there is no activity happening in the synaptic knob to allow the presynaptic cell to communicate with the postsynaptic cell. And if you don't know what a presynaptic cell is versus a postsynaptic cell, notice, pay close attention to the name. Presynaptic cell means that this is the guy who comes before the synapse. He's the one who is doing the communicating. He's the one who will ultimately release a neurotransmitter to speak to the postsynaptic cell, who is on the other side of the synapse, who's waiting to receive communication. So backing back up, the action potential has not reached the synaptic knob of the presynaptic neuron. And once that action potential does really reach the synaptic knob of the presynaptic cell, once it reaches there, then what's going to happen is it's going to stimulate voltage-gated channels that specifically are designed to allow the calcium outside of the cell to come inside of the cell, and therefore doing something totally different than what we've seen in the past, which is, kind of just sitting there. So as we continue along, it says that you have calcium that binds to the proteins of the synaptic vesicles, and this triggers a fusion of synaptic vesicles with the neuron plasma membrane, and the neurotransmitters are then released into the synaptic cleft by exocytosis. It's facilitated by numerous proteins. They diffuse across the cleft, and they bind to specific receptors on the cell to be stimulated. What did all of that say? Basically, what it's saying is when that action potential travels down the axon of the presynaptic cell, the presynaptic neuron, that action potential arrives at the synaptic knob. When it arrives at the synaptic knob, that electric charge hits those voltage-gated channels that are stimulated by an action potential. Those voltage-gated channels therefore open, and the only thing that they're allowing into the synaptic knob are calcium ions. The calcium ions then are now floating around in the synaptic knob, and there are these membrane-bound bubbles called vesicles. And these vesicles are special little bubbles that contain neurotransmitters. But these bubbles actually have little proteins on the surface. These proteins, if you can imagine a keyhole on a door. Calcium ions act like keys, and the calcium ion keys stick into the keyhole of these protons on these proteins on the surface of these synaptic vesicles. The calcium then sticks into the keyhole, and then it turns, and then what winds up happening is it stimulates the synaptic vesicles to then move towards the cell membrane of the synaptic knob, and then it causes these synaptic vesicles to fuse with the plasma membrane of the neuron's synaptic knob, and when they fuse, they empty. Once they fuse, they become one. They become one. That bubble becomes part of the wall. But when he becomes part of the wall, his contents are then released to the outside of the cell. And when these contents are released outside of the cell, this is the process known as exocytosis. Exocytosis is when the cell physically removes something that was inside of himself to the outside, usually utilizing something called a vesicle. And so those neurotransmitters that have been dumped outside the cell then float across the synaptic cleft, which the cleft is the space within a synapse that exists between the presynaptic cell and the postsynaptic cell. There is an actual physical space. We refer to it as a synaptic cleft. And those neurotransmitters sprinkle like rain right across the synaptic cleft, and then they bind to the receptor sites on the surface of the postsynaptic cell or the postsynaptic neuron. So that brings us to slide number 3, which, remember, I promised you that we would be looking at slide number 3, and lo and behold, here is a picture of a neuromuscular junction. Now, why is this important? Well, for those of you who are currently studying the nervous tissue chapter before you get to the muscular system chapter, this probably makes no sense, because you've been looking at one neuron talking to a second neuron, and it's like, oh, this is sacrilege. I can't believe that there's something else other than a neuron talking to a neuron. Well, get over it, because this is the way your body works. For those of you who have been talking about the muscle tissue before you got to the nervous tissue, you should be elated and excited, because in this picture you can see there's the axon up there at the top of the screen. There's the axon coming from a motor neuron, and then here are the telodendria, these little extensions off of the axon, and then here are the synaptic knobs right there at the very, very end. And these synaptic knobs, you can see that there's an individual synaptic knob for each skeletal muscle cell. And if you zoom in really close here, take this box and you blow them up, you can see the synaptic knob, and he's coming into close contact with the surface of a skeletal muscle cell. Now, in this case, this neuron would be the presynaptic neuron or the presynaptic cell, and this muscle cell, the skeletal muscle cell, would be the postsynaptic cell. And so here we go. There's an action potential. He travels here. He gets down to the synaptic knob, and then that action potential then comes into contact with these voltage-gated calcium channels, and the voltage-gated calcium channels open in response to the action potential, because the action potential has been bringing positive ions flooding into the cell, and this sudden change of positive charge around these voltage-gated channels forces these voltage-gated channels to let calcium in. Calcium then enters into the synaptic knob, and then it binds with these surface proteins on these synaptic vesicles. Now, inside these synaptic vesicles, if you look very closely, you'll notice that there are these weird little orange-looking things, and these little orange little things that happen to be inside here are actually neurotransmitters. And so when the calcium ions bind to the synaptic vesicles, it causes the vesicles to get mobile. And the vesicles begin to move, immediately move towards the wall, the cell membrane. Because see, the synaptic knob is a part of the overall neuron. It's not a separate thing. It's actually part of the neuron. Just like your hand is a part of your body. So Jim's hand is still part of Jim. It's just as much part of Jim as Jim's face. But we don't call it Jim. We call it a hand. You know, it's like, hey, Jim, hand me your Jim. No, that's not what we say. And that would just sound wrong. But we say, hey, Jim, hand me your hand. Well, in this case, hey, neuron, hand me your synaptic knob. And so the vesicle merges with the cell wall of the synaptic knob. And when it merges, it says, hey, look, we got stuff inside of us. Oh, well, then we'll just dump what we have outside of us. And it dumps those neurotransmitters, and those neurotransmitters float across the synaptic cleft, and then they wind up binding to receptor sites here on these receptors. And when these receptor sites acknowledge the neurotransmitter, these chemically gated channels then open and allow sodium ions into the actual cell. When we want to get rid of this neurotransmitter, what we wind up doing is we wind up releasing oftentimes like acetylcholine. With acetylcholine, we wind up releasing an enzyme known as acetylcholine esterase. And acetylcholine esterase comes in and snaps this neurotransmitter in half. And we recycle half of it back into the synaptic knob, and we throw the other half away. In a person who has Parkinson's disease, the primary neurotransmitter that you would find inside these synaptic vesicles are the dopamine. And with a person who has Parkinson's, they're not producing enough dopamine to release into the synaptic cleft to actually elicit a strong enough response on the postsynaptic cell for you to have a manageable result. So what winds up happening in some cases, not all, but in some cases of people with Parkinson's, what's happening is the neurons who are supposed to be building, who's supposed to be putting together more neurotransmitter, they don't have enough supplies. They don't have enough ingredients to make whole dopamine molecules. So when they dump what they have over here, the dopamine molecules are incomplete, and so they don't bind to the receptors, and then we have a problem. Okay, so that's about it. I mean, really, that's all what's happening at a synapse. An action potential arrives, stimulates the calcium channels, which are voltage gated. They respond to the voltage change of the action potential that arrives. The calcium comes in, it acts like a car key, goes into the ignition of the proteins that are on the surface of these vesicles. Those vesicles then drive over to the cell membrane of the synaptic knob. They open up, they release the neurotransmitters. The neurotransmitters float across the synaptic cleft. They bind to receptor sites on the surface of the postsynaptic cell, and then that's it. And that's it. I mean, literally, as promised. Like I said, I told you, hey, I was going to keep it down to 3 slides, and that's exactly what I've done to be able to explain to you what's actually happening at a synapse. So, don't know why my screen isn't changing back to normal. You guys are probably seeing me normal right now, but regardless of that, hopefully we'll return shortly, and we'll have some more videos up. This time I want to kind of talk, next time I actually want to talk about a neuromuscular junction, and I want to talk to you guys about how the process of an action potential getting inside of a muscle fiber, and then I also want to get into the process of getting actin and myosin acting together inside of a muscle fiber. So without further more of anything else, whatever that means, I guess I'm getting tired. I'm ready to eat, man. It's late. I'll holler at you cats later. Peace.